Hi and welcome back. In this video we're going to talk about queues and stacks again, and we're also going to introduce a new concept that is very popular in programming but can sometimes cause a bit of confusion. Let's recap queues and stacks first. You remember this diagram from before and how in a queue you add new elements at the end, and when you remove an element it always gets removed from the start. This is just a queue, like a queue for the supermarket, for example. And a queue in Python we can implement using lists or using the deck module or the queue module as we've seen before. Here's a simple sample implementing a queue using lists. Here we've got our class queue. When you create a new object, it sets self.items to be an empty list, and then you can push and pop. Push and pop are two names that are frequently used in the context of queues and stacks. I'm not really sure why these names are exactly used, but you can think of it as, adding a new element and removing an element. And depending on whether you are working with a queue or a stack, the adding or the removal is going to happen in a different place. Here, when we push in a queue, we append an item. So we add a new item at the end of the queue. And when we pop, what we do is we create a temporary variable called head and set it to be self_items0. And then we set self.items to be self.items starting from the value 1. And then we return the head. This is not a very reliable solution, by the way. What happens if you only have one item, say? But I just wanted to illustrate how a queue might work if you were to implement it yourself. Just append at the end and remove from the start. And this is sort of how you'd use it. You create a new queue object, and you can push values to it. Let's push 5, 7, and 11. And then you can print the result of popping, and that is going to sort of print out 5 at first, and then it's going to leave 7 and 11 remaining in the queue. You can pop again, and that's going to sort of remove the next item from the list and print it out, and leave your list with only 11. With a stack, it's slightly different. This is a stack, and you can remove elements from the top, and when you add another one, it goes back on the top. So the oldest elements are always at the bottom, and newer elements are at the top. And again, implementing this in Python, you'd have here your class stack, which again defines self.items to be an empty list. When you push at the start of the list. So we are saying that self.items now is a list of only the new element, which is the parameter, plus self.item. So that's going to join the two lists together. You're going to end up essentially adding an element at the start, and pop is just going to do self.items.pop. And as you can see, lists allow us to pop, and that just sort of removes the last element from the list and gives it back to you. So the stack pop and the list pop really do the same thing. And again, now you can push, but notice how when you push 5, you get a list of only 5, and when you push 7, the 7 goes in front. And then you push 11, the 11 goes in front, and as you pop, you start removing from the front as well. So you're adding and removing from the same place. We've already seen queues and stacks. I just wanted to give you a little bit of code about how they work, because what we're going to talk about next is something that I find really interesting. And that is the concept of how many steps does it take to find an element in a queue or a stack or a list. Let me go through it, and I'm sure you'll understand where I'm coming from. We can say that these queues and stacks and lists and many other data structures as well are what we call sequential. You start looking for elements at one end, and you go through until the other end. So if you are with a queue, you start at the first element, then you move on to the second one, third one, and so forth, until you reach the very last element. This means that if you're looking for an element in the middle, you have to go through all the elements along the way. So it can be really useful to start looking at one end, and then go through each element until you reach the last one. But it can also be quite slow. Let's say you wanted to only get the last element. You can't really do that with a queue unless you first pop all the elements that came before it. Here's another example. Let's say you have a long list, a very long one, and you're looking for a specific element. For example, this list here. Let's say we're looking for the element 90. Well, as you can see, we had to do a bunch of jumps. We've got going from 13 to 56, 38, and so forth until we reach the element number 90. This is because a list is sequential. If you're looking for an element, the only thing you can do really is start at the beginning, or maybe you can start at the end if that's more suitable. But either way, you have to start at one end and go through each element until you find the one you want. So this can be quite slow. It would be nicer if we could just know where the element is. But of course, with a list, you can't really do that. The number of steps we've had to do is quite a few. Our list here has 21 elements. You don't have to count them. Just believe me here. So let's say that an arbitrary variable n is 21. If we wanted to find the very last element in this list, we could go from the start through each element until we reach the last one. So we have to perform 21 sort of jumps. We have to sort of jump into the first element, then jump into the second element, then jump into the third element, and so forth. That means that for a list, which is a sequential structure, finding an element can take us up to n jumps, where n is the number of elements in the list. Notice that it says up to n jumps, because of course if you're finding the first element, that's only going to take you one jump. But if you're finding the last element, that's going to take you n jumps. And there is a specific term for this. When it takes you up to n jumps to find an element in a structure, this is called, what we say is that this structure has a complexity of O(n). Okay, that's just the terminology. O means complexity of, and inside the brackets we put what the complexity is. And in this case, the complexity is n, because we need up to n jumps to find an element. Okay. This is called complexity. So again, a complexity of O(n) just means that we need a number of jumps equal to the number of elements. Nothing terribly complicated there. When you're finding an element in a list that you need to jump n number of times, that's an O(n) complexity. And we're going to look at more into complexity in the next few videos, as well as how we can sort of reduce that, hopefully. But of course, instead of n, you can have other things in there. For example, O of n squared means that you need up to 9 jumps to navigate a collection of 3 elements. 3 squared is 9, so this is what O(n squared means. Of course, you can see immediately that this is going to be slower than O(n). With O(n), and you have a list of 3 elements, you need to make 3 jumps. With O(n squared), if you have a list of 3 elements, you have to make 9 jumps. And you can have the opposite, O of log 2n, which means that we need to do up to 3 jumps to navigate a collection of 7 elements, for example, or indeed 9 elements. So the thing inside the brackets is, you can think of it for now as the number of jumps in order to reach the last or the most far away element in a collection. In a list, the most far away element is the last element, and you can need up to n jumps to get there if you start at the beginning. And there are other structures that are not lists where these other types of complexity applies. We're going to look at them throughout the section. And don't worry if you're not sure what, for example, log 2n means. I'd encourage you to look it up, but that is as complicated as it's going to get in this section. We're not going to go into complicated maths. I'm not a big fan of maths, not very good at it. So we're not going to get into complicated maths. Just log 2n is the most complicated we're gonna see. So don't worry too much if you're not too sure. It's all going to be fine. Okay, hope you enjoyed this video. I'll see you on the next one.